All right. Oh, we're good to go. I'm going to go ahead and get started. People can continue to trickle in. I do think people are kind of getting hungry. But so welcome to our panel. My name is Aeowyn Kendall from Aztech Geothermal. I'm just going to give you a very brief introduction of what we're talking about today, and then we'll get rolling. So we are doing geothermal test bores and thermal conductivity testing today in this panel. We have 4 wonderful panelists who are going to frame the topic and then go into some really interesting details and advancements for you. But first, just a couple of housekeeping items. So everything that goes into the microphone is what's getting recorded. Please, if you have a question, wait for the mic to come to you. And we will also wait until our panelists have the mic to answer the question. Even if you're right here and we can hear you, please talk into the microphone. Otherwise, we will just repeat your question. And we do have a little bit of time at the end for Q&A, but it might be a little less than we thought, so we'll just go with it. So first up, we will have Kortney Lull from Midwest Geothermal. She is a driller with a ton of experience to share with us today all about the importance of test boreholes, especially on larger projects, and drilling logs and how those really need to be accurate, all that good stuff, lots of other details. Next, we will hear from Dan Sergison of Salas O'Brien, who is a design engineer and can tell us all about the design aspect and the importance of having that test bore and that drill log and all those design parameters that then go into the engineering of the system. Next, we will hear from Jeff Spitler, who is from Oklahoma State and is highly involved in ICSPA. Don't let him be too humble and fool you. But he has a wonderful presentation that will cover the basics of thermal conductivity testing and the history of it, and really frame the topic and the parameters for all of you. And then we will finish up with Garen Ewbank of Ewbank Testing, who will tell us about some advanced thermal response testing that he's been working on. So with that, I will hand it over to Kortney.
Oh yeah, this is... I forgot they're attached to the little bell, and the little bell is mounted. So, my name's Kortney, and I'm with Midwest Geothermal. Just a little bit about Midwest. I have been with them since their inception in 2008. We are an installing contractor. We install closed-loop geothermal systems across the U.S. So we've been in New York. We've been in Massachusetts. We were involved with the Framingham pilot project. We've been in New Jersey, California, Washington, and kind of everywhere in between. I am an ICSPA accredited installer, more years ago than I'd probably like to count. I am also on the ICSPA Board of Directors, have been since 2020, and also serve with the Michigan Geothermal Energy Association Board of Directors. So test bores. We need one. Who does what? So as a drilling contractor, I don't like taking on the liability of a lot of stuff, but we're going to need a few other people involved. Generally speaking, historically, we say it's just a drilling contractor and a geologist, a testing agency, but anymore, I like to say that we actually need a geologist involved. Honestly, I would really love to see test bores included with any of the geotechnical stuff that's being done on a site. Why? Because they have way more information about what's available subsurface. What we're going to drill through, we're going to call like gravel, or we're not going to get very specific on the details, especially in that shallow depth. So using a geologist or working with who's doing those soil borings would be great. I only have 3 people listed, but there's so many more people involved, right? Including the authorities having jurisdiction that are going to permit these holes, who are going to tell us what we're allowed to do. Thankfully, now we can go deeper than 500 foot in New York. But then what do you look for in the people that you're hiring to do this? You're looking for testing equipment and a company that's going to analyze the data, that calibrates and takes care of their equipment themselves. We are drilling contractors. I don't know how to calibrate their sensitive equipment or what it's supposed to do. We just hook it up and run the test. But then you're also looking for a driller that's capable of drilling productively to the design depth. Why do I say that? Importantly, and I repeat myself 3 times, capable of drilling to the design depth. Why do I say that? When we use drilling contractors that aren't familiar with drilling to our design depth, we don't get a lot of good information on the drill log. Sometimes those holes will take days, if not longer than days, maybe weeks. that information isn't all that relevant to those of us that will bid the job productively, because the information isn't available to us as to what it actually takes to drill that hole in a productive manner and a repeatable manner. And what does that mean? Risk to drilling contractors who are going to bid that work. And risk ultimately means maybe a less accurate drilling number. Maybe we have to put a little bit more risk on that number, so it's going to be a little bit higher. We're also looking for drilling contractors that are familiar with the area and utilize a more common drilling technique. So when I say that, air or mud rotary or air hammer are the most commonly available drilling techniques. When we use techniques that are not overly available, and especially if we don't include those in the drill log, that is my least favorite conversation, is going to be a change order. Because if someone drilled, let's pick on sonic, let's say someone used a sonic rig to drill a test bore and didn't tell us. The thing I won't know is that sonic rig, because it doesn't necessarily know, encountered a void. We've had this happen in the middle of the country. Test bore looked amazing, competent, it was awesome, 300 feet. We got to 150 feet and hit a void we could not get past. We actually don't know how deep it was. Our best guess was 50 feet. We couldn't overcome that productively. I mean, we could have pumped grout into that hole forever and never filled it up. So we ended up having to look at a hybrid solution because we just couldn't get past that. But because they used an uncommon drilling technique and did not indicate that on the drill log, it ended up being kind of some heartburn for that project. So as much as these test bores are really important to help validate the design, which Dan will talk about, for a drilling contractor, all of this information is vital to make sure that we know what we're getting into, frankly, and then we can avoid the change orders none of us actually like. So it leads into a drill log, and I have a cool picture of a rock. And I'll tell you a story of a job, although it's not the rock that I'll tell you the story of, which the rock is cool. We ended up having to use 2 excavators to lift it out of the hole because it's so large, but we drilled a perfectly straight 6-inch hole right through the middle of it, and the driller didn't know, they just thought they hit something hard. Didn't know it was a giant boulder that we ended up pulling out of the trench. So the story I'll tell you is that we drilled a project on the West Coast actually. We hit, drill logs had some gravel, some clays, something we could pretty well overcome, drilling mud rotary. We start drilling, we're losing tooling in the hole, things are not productive, things are not going well. We don't get it, because we're getting kind of what the drill log says coming out of the hole. They start digging basements, and they're pulling out 16, 20-inch, 24-inch boulder. That's a whole lot different to drill through, especially when, like the big boulder you see here, I can kind of tell that, or I can drill through it. Some of that mid-sized cobble, we just end up shoving it up against the drill rod. It pinches the drill rod in the hole, becomes a big problem, right? That's where I say working with those geologists or working with the soil boring companies is great, because they have so much more information about the cores that they're taking in that shallow subsurface. We would have known way more information had we had that from that drill log. Again, also what we're looking for is an accurate description of anything subsurface. Everyone's least favorite subsurface thing to deal with is gas. If you're drilling with a technology that may not tell you that there's gas present, and that's not indicated on the drill log, and then someone goes in with a technology that's going to bring all that gas up to the surface, again, problems, right? And gas, again, water is a problem, right? Like if we're going to discharge thousands of gallons of water, that's something to overcome, but that's not quite as dangerous as when we discharge gas to the surface and then someone uses a torch to try and fuse a loop shut and things get on fire, right? But that's why it's so critical to make sure that this information is accurate on the drill log. And again, drilling method, making sure that's on that drill log that we're giving out to the drillers. Importance of a test bore: location, location, location. Ideally, the test bore is going to be drilled in an area that we can use in the bore field. Honestly, the test bore is an investment in the project. We want to see if we can use it later in the actual project. So we want to make sure that it's within the general area of where we're going to drill the bore field. If it can't be used, like the drawing shows, show us where it is. Show it on the drawing, indicate that we're going to use it in the circuit or that we're going to abandon it. And honestly, on larger projects, more than one test bore is going to be needed. We're finding, especially in areas where formations are unconsolidated, that formations change. If we're looking at 500 boreholes, one tiny test, either in the middle or on the outside of that bore or that bore field, may not give us the best representation of what it looks like. If we have moving water across that bore field, not only as the drilling contractor do I want to know if formation changes, but as the design team, formation conductivity may change if water flow changes or if a million other things happen. So on these larger bore fields, consider looking at more test bores. And I would take them in different parts of the field. You know, don't do 4 test bores and just do them on the outside edge. We need to go across the bore field so that we really get as accurate of a representation of what that formation is as possible. Closeouts. So we drilled a test bore. As I mentioned, the test bore is an investment in this project. So we drill the test bore like a super long time before the building actually gets started. You need closeouts. You need information on that test bore that gives you like GPS information about where that test bore is. And ideally, we're gonna protect it, because like you see in this picture, we had an excavator who sheared it off. I cannot use that. So, unfortunately, that's a big deal. I have to go back to the client and say, oh, yep, can't use that test bore. I gave you all the stuff. I mean, even to the point where you could put temporary casing in it to protect it. We've even used colored casing so that it's very obvious, like, hey, don't touch that one. They're not inexpensive, so let's protect them as much as we can. And then a pressure test. Require a pressure test at the end of the test bore. It should be included in a drill log. We want to make sure that that loop that we're installing, that investment we're making in the geofield, is usable, it's viable, and that whomever is going to be awarded the full project can use that bore, and that when it was left after we've drilled the test bore, it was good to go. So basis of design. So this will lead into Dan's presentation, but as a drilling contractor, I'm not a real big fan when we drill a test bore to 500 foot and then I see the design documents come out to 850 foot. That I have no idea what's gonna happen in that extra 350 feet. Now, some places it stays competent rock, other places not so much. Or we end up with voids, or we end up with unproductive drilling now. That, you know, we drilled to 500, maybe it took 5 hours, but then we drilled to 850 and we hit a harder layer of limestone, or we hit something else. Now that drilling takes 2 days. When I did the test bore, I had a pretty good idea. Well, now add almost double that borehole length, I have no good idea, right? Not only that, but it changes so much. We have had drill test bores, again to 500 feet, right? And then we go to drill another test bore, because we're honestly like, that's not, you can't just change the borehole depth by 350 feet and expect everything's gonna be fine. So then we drill it and we go the extra 350 feet and we hit gas, or we hit more water that we can overcome, or we are stuck on something, again, a formation that it takes forever to get through. So now this project that was a super tight schedule, we could meet it at 500 feet, not a chance will we meet it at 850. Well, now they're, oh, well, you need to bring more drill rigs, you need to do all these things. It's like, well, time out. That's the part of the test bore, right? It's not just that we're doing the due diligence for the design team, validating design, making sure that they have all the information they need to design this field, but we're making sure that the driller has everything that they need to be able to accurately quote and install the job. And with that, I'll turn it over to Dan.
All right, thank you, Kortney. My name is Dan Sergison. I'm a senior geothermal engineer with Salas O'Brien. I've been doing work, I lived in New York my whole life, born and raised. Went to school in Philadelphia for 5 years, but other than that, I've been in New York the whole time. I live 2 miles away from here, literally able to ride my bike here this morning. So it's nice that NY-GEO has come down from Albany to, join us here in New York City. I've been doing this between a couple different companies since 2013, since I graduated college. I've been lucky enough to work on some really cool projects in this area. I've worked on, back when I was with PW Grosser, we were able to work on St. Pat's Cathedral over in Manhattan, 10 wells, 2,000 foot deep, all standing column wells. We were able to work on Obama Public Library in Chicago, so obviously not New York, a little far away, but some really good experience over the years, so I'm very grateful for that. New York GEO has been a great advocate for Salas O'Brien and for the whole industry in general, so I just wanted to thank NY-GEO. Also wanted to thank, before I get started, Nice Serda. I see Sue sitting front and center. Thank you for all the work you do. It really helps a lot of our projects get off the ground after the test bore. And I wanted to thank Con Edison. I know they're a big sponsor here at NY-GEO. But Con Edison, they've been incentivizing test bores, so they're giving up to $40K for test bores in New York City. I think 40K is the max, and then they also have the clean heat program, which helps after test bores. So I just feel obligated to thank them because all of them have been great partners. So I'll be talking about the designer's perspective on test bores. I only have 10 minutes. I could probably talk for hours on this, so I will try to keep it brief. So why do we do it? The obvious thing is getting essentially these three inputs that inevitably go into different kinds of geothermal modeling software. There's a few kinds out there. Not going to name them, but essentially this is really what we're after. We want these three inputs. Thermal conductivity, basically how much heat could you get in the ground or out of the ground. Thermal diffusivity, how quickly is it moving, the heat in the ground. And then the average ground temperature, it's pretty much your starting point for when you eventually have a whole geofield in there and you're going to be changing the ground temperature over the year. Ideally, it's balanced over the year, but I won't get fully into design. I'll stick to just test bores. Less obvious thing is to confirm and characterize the subgrade, observe and document drilling conditions closely. Drillers' logs could vary. This is not a knock on drillers. We absolutely need more drillers. I respect what they do. We couldn't do any of this without them. So I like to really keep an open line of communication with the drillers before leading up to a test bore when you're scoping it out. We like to be out there when they're drilling. I have a slide on that. I'll talk a little bit more about that in a bit. So not a knock on drillers, but logs could vary. I mean, Kortney alluded to it, glacial till, SP, if you're using, the classification system that they use in like geotech mostly, there's just a lot of interpretations. You don't know what kind of level of detail you're gonna get in a drill log. I mean, the drillers are literally operating expensive equipment, usually in tight spaces, especially in New York. So putting a very detailed drill log on them as they're drilling is a tough task. So we'd like to get out there to pretty much compare notes, get our own data, be able to not necessarily make decisions in real time with them, but just be, on the same page. Especially when it comes to water production, managing water on any site is challenging, whether it's clean water or contaminated. Hopefully that's not the case, but we like to do test bores to really understand how much water is going to come out of that formation. We like to do it as well to understand the casing requirements. Casing is expensive. It keeps the overburden out, so it keeps the hole open in many cases, depending on what you're doing. But we like to understand how much casing you're going to need, because that's really going to change your the cost of the job, and hopefully not enough to take it off the table. The much less obvious reason we do test bores is to measure the speed, the penetration rate, basically minutes. How many minutes does it take to put a 20-foot drill rod in the ground? I mean, drillers are, doing a lot on site besides just drilling. So we like to get out there to literally, drillers will probably roll their eyes at this, but basically get the stopwatch out for that drill rod. How much time are that, is really, not to do a gotcha to the driller, but really just to understand how long is it going to take to get this thing in. So what else is here? Mud rotary versus air rotary. I mean, hopefully going into the test bore, you have a good idea of what you're going to do prior, but sometimes you might go into something thinking you're going to need air rotary, and turns out you don't. So maybe, test bore is a good chance to maybe make that change for when you come back to do the full bore field. How many for a project? This is, I consider, open to interpretation. I tried to look up the old GSHP guideline from years ago. I took my textbook out, couldn't find it. But I think it was about 1 test loop per either 50 or 100 tons of connected load, which I use, it's a reference point. But personally, I feel it is very site-specific, depending where you're drilling, how deep you're going, the conditions of the site, how big is the site, a few different things. So usually we will specify the quantity, and we will also consult a local driller on this too. So it's an open line of communication leading up to the actual drilling of that. And a couple examples, we've only done 4. At Obama Public Library, we specified 4 test bores for what inevitably was 240 in total. It's a 19-acre site. And we did follow this GSHP guideline at the time. And I just wanted to provide that. And then we've done Epic Systems. It's a massive geothermal site in Verona, Wisconsin. most of you hopefully people have heard about this one before. It blows my mind how many geothermal systems they have there, both open and closed, lake, you name it, they got it. But it's 1,100 acres, and they've only done 4 test bores on that site. Mostly it's a function of the geology there. You know, it's a big open field. It's known that the geology does not change that much, so we didn't really feel the need to do a test bore every time they're adding a bore field to that site, which seems to be all the time. And the data up on the right in blue, that's just the TCTD and the ground temperature that came out of the 4 test bores at Obama Public Library. So this is in Chicago, not quite New York, but as you could see, those 4, that's the range provided for those 3 measurements. They're all pretty damn close to each other. So I just, it's interesting to see that data. And it looked like the better numbers were closer to the water. So Obama Public Library, it's right on the lake. So we got a little bit better numbers the closer to the lake that we got. That was just an observation from it. And then 2 local projects at the bottom. Again, I know it's NY-GEO, but these are 2 Jersey projects. So right across the Hudson River. Just an interesting observation in doing this. We look at the geotech report. Geotech equipment, different than drilling equipment, or geo-drilling equipment, I should say. So we look at the geotech, it says there's weathered bedrock 155 feet below grade. So, that's kind of where we expect to bottom out if we're going to set casing or not. Turns out when we went to do the test bore, they didn't hit competent bedrock till 300 feet below grade, so much deeper than we thought. Similarly, in Jersey City, just 1 mile north of the Hoboken site, competent bedrock, according to the geotech report, was 75 feet. Got out there, Allied just drilled it a couple months ago, and I was out there to witness it, fortunately, and you could tell just the way that the rig operates. They hit it pretty much at 75. It got a little denser at 80, so they were able to set casing and continue drilling right after. So just 4 projects I wanted to include that, you don't really know what you get until you really start looking into information, which leads into this slide. How do we do it? We consult as much information as we can that's published on the site. States keep records differently, so I don't always rely on state records. New York's aren't great, but I usually find myself falling back on the USGS, so United States Geological Survey, federal. It applies obviously all over the US, but they just 2 months ago, they released a report they've been working on for a couple decades. That's the hydrogeologic framework of Western Long Island, so literally where we are now. It doesn't include Manhattan, but believe it or not, Brooklyn is part of Long Island. So a lot of good information in there. It tells you depth of bedrock, and that's my number 1 source for information, USGS. Hopefully they attended this, or they're going to start, because they do a lot of work that I feel goes underappreciated. So when we do test bores, we try to invite USGS to join. So after, so like they drill the test, they just get the bore in, we would call USGS prior to that, but then they would spend a day or 2 with their own equipment, lower it down the hole, do a whole geophysical log, give that to the client. So, it's not quite free. They don't charge for it, but you got to pay for the time between drilling the hole, having them log it, and installing the loop, assuming it's a closed loop. You do have to budget for that, but you do get really good information. USGS will give it, and we like to invite them to our sites. I know I'm running up against time here, so we like to create a RFP package with all of our requirements for a test bore, similar to what I had just talked about. Get different prices from drillers. Best, that's the best for the client, best for the project. Kortney mentioned it. We don't like to specify our bore field depth any deeper than the test bore. I think it comes up a lot now because of the 500-foot rule, and it's great that we could drill deeper than 500 feet, but some people are like, oh, we have one at 500. Could we just do the entire field to 850? And no, you can't until you do a test bore. That's my take on it. I'll run through this real quick, but this is essentially a list of all the stuff you're missing if you cannot observe the driller. You want to get out there, see what they're doing, not to catch them doing anything wrong, but just to get literally all of these items that otherwise you wouldn't be able to get. Speed, how much time it actually takes to drill. You could grab samples of the cuttings if you want, observe the equipment, quantify groundwater, see how long it takes to trip out, pull all the rods out, confirmation of this entire list that I won't go through, and things that we want drillers to call us about if they can't reach the target depth, why, what were the conditions leading up to it. Other unexpecteds, like a lot of groundwater production, going through large voids with like sonic, let's say, like Kortney had mentioned, when they're tripping out, when they want to set casing, we just want to make sure that, we don't want to tell them exactly how deep, but we want to kind of just have a discussion before they get to that point. I'll probably skip over this one, but this just shows the urban heat island effect. This is from 555 Greenwich, the job that Tony Amos from Endurance talked about yesterday. Basically, y-axis goes down 100 feet. This is in Soho, so right in Manhattan, across the water. And as you can see, the urban heat island effect is very present. Basically, you're at 73 degrees when you're at the surface, and you don't really get under 60 degrees till you're about 100 feet down. That's just from literally centuries of, development and increase in, impervious pavement, buildings, concrete, all that stuff. So another reason to, you just want to check with the test board what the temperatures are. And I'll probably skip those last few. So sorry that went a little long. But yeah, Jeff Spitler's up next, and yeah, thank you for coming.
Okay, I'm Jeff Spitler. I'm going to something completely different. I'm a professor of mechanical engineering, and we started working on this in 1994. And I'm going to talk a little bit about history and some of the basics. Some of you know I developed GLHE Pro, and in fact we released the first version 30 years ago. And any kind of design software, what we found is that it creates demand for more information that we didn't have before. So one of the things, of course, we had a place you could enter thermal conductivity, but the question is, well, how do you get it in practice? So if you look back to this figure on the left from 1989, this was the IGSPA and EPRI soil and rock manual, and you see these bars representing a range of conductivity. So if I marked out the limestone conductivity, if you just take that range and just like I took a medium office building in Atlanta and sized a ground loop for it, took the total drilling, you can see the difference between the lowest conductivity and the highest conductivity is about 44% in terms of the total drilling required. So we'd really like to know, because we don't want to spend 44% extra and we don't want to be 44% short. Right? So the original idea goes back indirectly to what's called a needle probe. So this is a 1931 Swedish paper on a new method for measuring the heat transfer coefficient, the conduction coefficient. And in a way, some of you may have used these tests. I have a small little briefcase size one with I think it's a 6-inch needle or 8-inch needle that we stick in a sample if we want to measure the conductivity. It's the same physical principle. But we started on this in 1994, and turns out there's a group in Sweden that started about the same time. So in fact, two of the people that were involved early on are right here in the room. So Trey Austin is a graduate student who actually built this trailer. You see that says OSU and all the stuff inside, and with a little bit of trial and error on a few things. Yeah. Right, and Garen Ewbank over here built a commercial trailer very quickly and brought it to OSU, and we tested it. So I can remember a few stories, but we're short on time, so I'll go on. So the starting point for both the Swedish group and OSU was a paper by a guy named Paulne Mogensen. And Paulne's paper actually, in 1983, actually was proposing a method to measure the borehole thermal resistance, not the conductivity, but you get the conductivity before you get the thermal resistance. So the top trailer, that's obviously the OSU trailer. The bottom figure there is a Swedish trailer called TED. And TED doesn't stand for anything, it's just what they named the trailer. So And the person who named the trailer, that's right here on the right, is Singhil Jalin from, at that time, Luleå Technical University, and Paulne Mogenson's in the middle, and that's me on the left, some 16 years ago, or 15 years ago. So the idea, right, is that you use a test borehole, you put a U-tube in, you put a constant heat flux on the borehole, and you'd really like to make it as constant as possible. And almost back in the 90s, when people started building test rigs, you could often tell how much experience they had by how much insulation they put around the tubing. So I have a photo of a test that Trey and I did in the Dallas area. You know, we had a little bit of like pipe insulation about this big around, and then you see the later test, and we've got this aluminum foil duct, you know, fully full of insulation, because it was difficult to get a good constant heat flux. So if you put that constant heat flux on the borehole and you measure the temperature response, you can back out the thermal conductivity. So the original theory comes from Ingersoll and Plass in 1948. I guess since I'm a professor, I had to put in a differential equation here, but basically what it says is that the conductivity is inversely proportional to the slope. So the higher the slope, when you plot the temperature rise versus the log of time, the higher the slope, the lower the thermal conductivity. So this is a test we did about, I think, 9 years ago or so, and I've tried to break up, you know, starting at 10 seconds all the way up to somewhere over 100,000 seconds, and roughly break it up into, there are effects of transit time through the borehole. There's the borehole itself dominates the heat transfer in the early hours, and so it's common to use the time after 12 hours for analysis. And what Mogensen did is, to measure the thermal resistance, he took the slope, the line that you used to estimate the conductivity, and then drew in what would be a zero thermal resistance line. And if you know the undisturbed ground temperature and the mean fluid temperature, this difference then can give you the borehole thermal resistance. So actually it's very important to measure the undisturbed ground temperature, and particularly in cases like Dan showed where there's, I couldn't see the slide, but where he showed this urban heat island effect, right? You can't just assume the temperature is the lowest temperature you get or something like that, or highest. So the early test rigs, we suffered some from transient heat output due to environmental effects. The generators we used weren't necessarily very good, or we had utility voltage fluctuations. So, and that's why I mentioned we used extra insulation. But even later test rigs, so when we did this much more carefully 9 or 10 years ago, we have a pretty constant heat output, so it's about a plus minus 2% from the average. If you make an estimate of the conductivity starting, say, at 12 hours, here using 12 to 48 hours, and then you maybe do 13 to 48 hours, 14 to 48 hours, 15 to 48 hours, you'll see you'll still get some variation in the estimate of the conductivity. So one approach that we took to try to deal with this was to use what's called parameter estimation. And talk a little bit about parameter estimation in a minute, but our first estimates of uncertainty under field conditions were on the order of plus minus 10%, and I've never seen anything since then that suggests that it's, you know, you can get, under normal field conditions, can do a lot better with a sort of normal thermal response test. So what parameter estimation does is it basically matches the curve, right? So the orange here is what we measured for the temperatures, the mean fluid temperature, and the blue here is the estimated value. So you basically adjust the fit by finding the minimum of the sum of the squares of the error, and this is an example of that domain where you're searching for the lowest point on this surface, which for us is the soil conductivity on one axis, and we use the grout conductivity as a surrogate for borehole thermal resistance for reasons I could explain later if you're interested. So we did some validation early on. We measured cord samples and took a number of measurements of different samples from different layers. We used a sandbox approach on the right, so we had a pseudo-test borehole. And with everything controlled very carefully, we could get within about plus minus 2.5% of the values known. So, but still would estimate as being plus minus 10%. And so the thermal response test or thermal conductivity test, TC test, I'd say it's well established at this point. It's come a long way since we developed the early methodology. We have more compact test apparatus, lots of experience. There's been a couple developments, say in the last 10 to 15 years, which is a distributed thermal response test using fiber optics that can measure the conductivity of the borehole along the length and give you some idea if, for example, the conductivity gets better as you go deeper, maybe like a deeper borehole, or if it falls off, maybe you don't need to go to 500 feet. In the references, there's a couple PhD theses from the Royal Institute of Technology in Sweden. And then the other development more recently has been some thermal response tests that measure the thermal diffusivity or volumetric specific heat and conductivity at the same time. So one approach is this oscillatory test where instead of posing constant heat flux, you have a constant heat flux and then superimposed on it a sine wave. So you vary it up and down. And our next speaker, Garen Ewbank, is actually going to talk about a different approach to measure this thermal diffusivity. So thank you. Come on up, Garen.
Okay. Well, good morning, everybody. It's almost noon, though. I'm looking at Jeff, and I know he's hungry, so we'll try to get this going. First thing I want to say is we are amongst some really good people. Of course, Dr. Spitler, and then Trey Austin. We've been in this deal for a long time, haven't we, Trey? Anyway, as we go through this, I am Garen Ewbank. I am the owner of Ewbank Geotesting, which does thermal in situ testing. Nick's Temp Solutions, which has a couple of patents on some new type of heat pumps that are out there, polymodal and modulating multi-source. And then the Gray Edge Group, I'm founding and managing member of that group. But the real story is, about 10 years ago, I set out to try to bring everything together because I realized at some point the value of the ambient temperature loop or district system or community systems was going to become really critical. And to do that, the ground heat exchanger changes from the primary sink source to other things, all right? And so to be able to manage that as a thermal battery, we needed to know what the volumetric heat capacity of the local earth is. So we can get the thermal conductivity, we can get the deep earth temperatures, but we have to really know how that thermal battery is going to charge and discharge minute by minute, hour by hour, day by day, season by season. So as we go through that, things are really moving forward, and that's why we set out with these three different companies to offer some changes to our industry, which, you know, is a pretty good deal. A little bit about myself. At OSU, we have a board called within the College of Engineering, Architecture, and Technology, which the dean puts together, and he has some of us come in every once in a while, and we talk and speak, and we see where the university is going to go, how our students are doing, and maybe some changes that are coming down the road. So it's a pretty fun deal, okay? I did graduate from there in industrial engineering, Jeff. I apologize for that, you know. But anyway, I'm a full member of ASHRAE. Within the Association of Energy Engineers, I'm a life member and hold the rank of fellow and 7 certifications and a lot of stuff. At IGSPA, I train all the classes and all the courses, and even the new ones. We got 2 new ones that are coming out, and so it's going to be a really good thing for our industry. All right, so I'm going to talk about the advanced thermal response testing. And we're doing a numerical analysis and running a digital twin, and it's based on the resistance capacitance understanding, which Jeff has done, you know, quite a long time ago. But we've taken it to another level, and particularly with the digital twin as it's running. All right. So this is a little model of what it looks like. But Rick Clemenzi, he's a electrical engineer, PE, and I set out to figure out how we're going to get this volumetric heat capacity. And so we know that the diffusivity is simply a ratio of the conductivity, thermal, and the denominator is the density and specific heat of the local soil. Now, we got a lot of different lithologies that we drill through, so we're going to end up with averages, all right? So in the past, what we've done for the estimate of diffusivity is go to Kavanaugh and Rafferty's little book and pick out those, areas and try to mean it out and go from there. And you're going to see here in a little bit why that doesn't always work. And that's been what the industry has done for years, okay? So as we go through this, Rick and I put together a little deal where we can do single borehole testing, ground heat exchanger testing, the whole system, okay, and cascading heat systems testing. That goes on down into some little hotter rock processes that we look at. But anyway, we can run this thing, and our power source for our heat can be electrical. It can be other, like propane. And so with that, if you have a good measurement of your flow and the temperatures, and you know that the temperature you're getting up here, you want to wait for it to come back over here to see its response. If you're doing it at the same time, you got a little misslope in that, but that's okay. We can get through that. So anyway, that's what that looks like. All right. So in single borehole testing, we found that we do not need to have steady power. Power variations are okay. In fact, they enhance the ability to see what we've got. And we can greatly reduce the testing time. I think Dr. Smith one time had an article about, you can on some boreholes get this in 12 hours. Well, actually we need to be longer than that for some stability. But anyway, we need to be able to do third-party verification. And what these devices do, and I've got a test running right now on the GNOME project in Saudi Arabia, and it's throwing its data up to the cloud. We start it, stop it, everything from a web interface. So I turn the heating elements on, turn it up, pump on, heating elements on, the testing, give it a name and all that sort of stuff. And then I've got one that's going on in Ohio right now that's online, and I watch it, and the test provider, I just tell him, okay, it's time you're done, okay. And so that's really helping us get the information properly. And so if your engineer record wants the older ASHRAE IXPA test, that's fine. It's actually probably a good idea, okay? But we can do that, all right? So if we get into the ground heat exchanger, this is new, all right? And reason I really looked at this is because I get calls a lot of times to do rescues on systems that are overheating, all right? And we did one, a little short story, but it was in Mississippi on a prison facility. It was a 600-bed hospital, okay? And the ground temperatures were getting up to about 101, 103 degrees. And they were saying, you missed the thermal conductivity value on this, okay? So here comes all the lawyers. Oh, okay, fine, okay. So I sent one of my partners down, and we found that the RTUs, rooftop units, had been converted from air source to water source. And they put the blower fan right near the reheat coil. So their airflow was terribly restricted. Their efficiency, which the project was designed with about a 3.3, and this was, quite a while ago. The machines were operating at about a 1.3 COP. Well, no wonder the ground was getting hot. We were ejecting a heck of a lot more. So anyway, those things you can find, and we'll go through that. So we can go through a lot of these deals. Don't worry about most of everything, but we do measure the grout thermal properties in real time, and that's a benefit to the drillers, all right? Did you grout it right? I know that there's a lot of samples that are taken out of the mixing better, and we've done some research on that. It's available at IXPA, but you'll find that not always the test that you get or report on the grout is accurately what's done, all right? So we can go through those things. We can go further into this, and This digital twin, guys, it's been around a long time. A lot of people are doing it. Yeah, it's just, computational time and stuff like that. But we can actually get in there and begin doing the heat storage and discharge and the heat rejection for auxiliary devices. We have some of those. And so when you get into a district loop or a common system, it really becomes important on how this is going to operate and how you're going to do it, particularly if we're going to do any demand response information. So we go through there and we look at all this other stuff. This stuff is probably not applicable to what you're going to be doing and seeing, but here's what the test looks like. And this is a normal response. It runs for 36 hours, just like the Astra IXPA test, all right? And then what we do is we start varying the heat flux. And so we drop off all the heat, let it rest, and then I'll bring in another heat flux, and then maybe another later, and we'll look at that at the end of that. And with that, we're gonna run a digital twin on that data set, all right? And luckily, Xiaobing Lu at Oak Ridge National Labs was the guy that oversaw what we were doing, all right? And he had some pretty tight, what did you say, Jeff? Error bars? Yeah, really tight. And we were able to do it very well. So it's just math. Anyway, that's what they look like. It's nothing complicated, but we want to make sure that we can quantify and directly measure that volumetric heat capacity. And here's one that's really important. This was done on a DOE project in Carbondale, Colorado. And the top part in the yellow is all you need to look at. That's from my original report. Thermal conductivity 1.69 is what I got, and estimated diffusivity from the drilling log at 1.18. When we did the TRT analysis on that one, the conductivity came out 1.66. That's well within the range. But here's where the big deal was. We found the thermal diffusivity at that location was not 1.118, it was 1.76, which means storing heat's going to be a little bit of a problem. Okay, and so we have to take that into account. So that's where I'm at. That's what they look like. And the last thing I want to talk about is the difference between developmental and exploratory drilling. Okay, when you do a test borehole, in Oklahoma particularly, I work with the Water Resources Board, we call that an exploratory borehole, and it's because of liability. All right. When you come in, and if somebody changes the depth to deeper, you're taking big liability, okay? So if, the engineered record says instead of 400 foot, we're going to 600 foot. Hang on, we've got to have a new test borehole. It's a big timeout deal, okay? If you then drill the ground heat exchanger at the no greater depth than the test borehole, then your developmental drilling and your liability is a whole lot less. And so we got to make sure that we follow those. And I like what he, Dan said about, hey, sometimes we change our minds, don't we? Okay? And it's okay, but if we're going to go deeper, we've got to have a new test. And guess what? Those tests are not an additional cost to the project. The in situ testing is, but the drilling is not. Okay, so it can be rolled right into the project. So we go through this, we look at those things and hope we can see that. So anyway, we've got some conclusions, and so summary. Who? Every commercial ground heat exchanger, all right? What? I'm talking about the advanced thermal conductivity testing. That's something new, and we've been working on it for a while. Before the ground heat exchanger is designed. And I know a lot of us, we go out there and we'll pick some numbers, okay, and we'll, plug in some TC numbers, some deeper, numbers, and some diffusivity numbers, and we'll do a preliminary design, all right, and it is preliminary, all right. But we can get to proper sizing and costing as we get more valuable information. And I want to also, what Dan talked about, the lithology or the drill log, that is really important. And sometimes you have to train your drillers to understand that there's a lot of different types of rock. okay? And so we want to make sure that we get that. We have what we do at the Gray Edge Group is one of our partners is a civil engineer PE and a hydrologist. And so he pulls the samples, and it's a great looking report if you ever see those. So anyway, that's who we are. That's who I am. Contact me, holler at me, whatever you want to do. Thanks.
All right, thank you to our panelists. We have 5 minutes for questions.
Is this on? Hi, Jeff Hoffer with Aztech Geothermal. We've recently, in the last couple of years, gotten involved in coordinating the drilling, doing the thermal conductivity tests. Seems like we have a lot of people that come in early in the process. We think we want to do geothermal. Can we schedule a thermal conductivity test? So I'd just question to the panel, what would you say is the proper time in a project to actually do that? You know, obviously we know we want to do it before the design, but you speak to when does it make sense to do the thermal conductivity test?
I would say the earlier the better. We had a job, that Hoboken information I showed, we, kind of Garen was just saying, we ballparked the TC without doing the test, figured out, I think we needed 72 boreholes, 850 feet to satisfy the building. Did the TC test late, because the client had to acquire the property. It was, they would have done it sooner, which is when, we wanted it as early as possible. But by the time they had done it, we had issued our construction documents. So we had to issue an addendum after we issued those documents. We were able to take 6 boreholes of those 72 off the project. And I think it was 40 grand per borehole. So doing it early always helps, and it saves a lot of frustration, but you could always do it later too, and you could still save money if you do it later. I mean, hopefully the timing works out, but to answer your question, as early as possible.
Yeah, and to go further into it, I think the idea that a lot of people think is it's a feasibility study. I'm not sure if I want to do geothermal, so the first thing I'm going to do is do a test board to help me decide if I want to do geothermal. So if you could speak to that.
So the design is really an iterative process, and each time you go through that, you may make changes in whatever you're going to do. You may decide to put some hybridization to the system, like wastewater heat transfer, solar PVT, whatever. But those all change what that design is going to look like. One thing that's new to the industry is we're now at ICSBA, we're teaching the Certified Geothermal Inspector course. And they're to be involved from the very front end, pre-bid, all the way through to turning it over and looking at it for 2 years after it's been running. And there's not a lot of time after it's turned over to the owner. Occasional, you'll go in there and look at it. But that process, with the toolbox that were given to those guys, there's some in here that's taken that course, and they've dug through that toolbox, and you're like, whoa, a lot of stuff there in there. Yeah, okay. So anyway, that would be one of the things I would always recommend, that on these larger projects, somebody that's a CGI be involved at the very start.
More questions?
Hi, I'm Austin with Aztech Geothermal. I was just curious, I know ICSBA has some base guidelines on when a test bore should be utilized to really ascertain whether or not the project's going to move forward or to really understand the ground geology. Is there any rumblings about like a federal mandate or any other kind of legislation that's supposed to be coming down that forces a test bore to be done before a project over a certain tonnage or size?
Well, if you follow the ANSI, CSA, ICSBA, C448, it lays all of that out. Okay, and that is part of what we teach in the CGI course. Right? Is it required? No, but the liability for not doing it is enormous. Okay, what might happen is it may be typically heavily over-designed in the ground heat exchanger and get thrown out on first cost. And that's what Dan kind of alluded to, originally. So, it's more of an economic deal than a mandate. But the process of actually drilling and testing a hole, there are codes and standards for that, okay? And everybody should be following those. And I think they do. All right.
All right, we have time for one more.
So Trey Austin, the question really is kind of maybe for everybody, but the standard off-the-shelf TC testing equipment with the heating elements that are there, the wattages that they're designed for and set up for, really only have a maximum depth of about 600 feet. And everybody's starting to do 600 feet and deeper, which means we're not really maintaining the ASHRAE standard of watts per foot that we're trying to get to. What adjustments, if any, have been made on these deeper test holes? Because right now you're not putting enough wattage into the test. Are you getting more wattage in some way, or are you just still using off-the-shelf stuff? Because the way I look at it, you may be getting some inaccurate results. And I'm not trying to point that out negatively. I'm just saying, because I'm being questioned to do deeper holes too. And I'm like, look, the TC test equipment's not really set up to do that. So what do we do? That's my question.
Okay, so the little box I showed you on our deal, there's 3 heating elements in there that are electrical if you use electric power, and they're 5,500 watts each. And so that'll get me a little bit deeper. If you need to go deeper than that and don't have a boiler that you're going to put on, electric boiler or something like that, then you can use propane or whatever's your heat source. And that's the reason we went to the propane for the heat source, additionally to get a lot more heat into that so I can see that flux and watch it as it comes up and comes down. And so with that, that gives us the ability to do the deeper test easily. Thank you, Trey.
Before I pass to the next question, I want to make sure that everyone got a chance if they wanted to take that one. Good. Kortney, you want?
Make sure your driller asks a question. I am not them. I just know I hook up a box, but I ask questions. So because of the liability that we take on doing this, I keep in constant communication with the company that we use to run our tests to make sure that the equipment that we have is adequate. If it's not, they ship me a different one. Because we are constantly being asked to go deeper, and the standard box that we keep in our office and they take back once a year to make sure everything's kosher is not enough. So we keep in constant communication, especially when we go past 500 feet, to make sure that the equipment that we're using is satisfactory, especially, frankly, now that we're looking at 2-inch U-bends, even more so to make sure that there's adequate pump to be able to pump the heat that we're going to pump into that U-bend to get accurate results. But I would make sure that your driller understands and reads what you're going to spec to make sure they're asking that question. Okay, so if there's drillers in here, talk to your testing company, especially if you're going deeper than 500 feet, because chances are it is not enough.
All right, Kevin.
Just kind of a general question. Kevin Moravik, Barney Moravik Incorporated, NY-GEO. We look at TC, TD, the engineers always want to see that information. There was the question about the feasibility of this. As a driller, we want the log, as Kortney has said. I care about how long it takes us to drill it. How much do you actually change a design based on a 0.1 or 0.15 variation in a TC number?
Not very much. We'll still run the calculations. It's really just to make sure your assumptions are correct from our perspective. That Hoboken project I mentioned, I think we were assuming 1.5 and it came back at like 1.95. So that's why we were able to adjust. But something that's small, I would imagine it wouldn't have a significant impact on the actual size.
And as a follow-up to it, because we always find it interesting, we're dealing with a clean heat program that the utilities administer, yet a lot of these bigger buildings are cooling dominant. And so what steps are we looking at to protect, let's be honest, the drillers, because we always get the fingers pointed at, it's the loop that's underperforming. It's never the design, it's never the distribution, we always start with the ground loop. So what are you looking at when your load is cooling dominant versus heating dominant?
we're looking to hybridize, so that could just be adding air source equipment. But our, the way that we design all of our projects is balancing the load on the ground and not setting it and forgetting it, but literally building the controls in to take those temperatures, those flows, and creating that sine wave for each year and seeing, is it trending up, is it going down, how could we adjust it so it's not a surprise, so the client isn't, they have a big event where they're filling a gymnasium or something, so that they could prepare in the short term, but also we monitor that in the long term to protect their investment. It's really an asset. You're spending all this money to put this in the ground. It's got to be mostly correct, but you could use the controls to kind of keep it on a healthy path for its 50, 100-year life.
All right, I'm going to release you all to lunch because I have already gone over. But please thank our wonderful panelists. And if you have another burning question, they'll be around for at least a couple more hours, so you can catch them.